This video looks at what is meant by the term invariant. When applied to scalars and vectors, it shows how the magnitude and direction of vectors are invariant under a coordinate change when their components are not. What do we mean by the invariance of scalars and vectors under coordinate transformations? Well, let's start by considering a scalar quantity such as the temperature T at some given point XYZ in a room. In the Cartesian coordinate system, the temperature of the point XYZ in the room is given by T as a function of its position coordinates, XYZ. But in the spherical polar coordinate system, the same point has coordinates r, theta, phi, and the temperature at this point is given by T equals T as a function of r, theta, and phi. Now, since there can only be one temperature at this point in the room, we must have T of XYZ is equal to T of r, theta, phi. So this is an example of scalar invariance under a coordinate change. Vectors. Now, vectors are a geometric object that possesses a direction and a magnitude or length. Now, the direction of a vector does not depend upon the coordinate system used. So a vector that points from the bottom of this page to the top does so irrespective of how we define our coordinate system. So the direction of a vector is an invariant quantity. The magnitude or length of a vector is an invariant quantity, so that a solid metal bar does not change its length when the coordinate system used to measure it changes. So the magnitude of a vector is an invariant quantity. Now this metal bar, whatever coordinate system you use, it's not going to change its length. So the length or the magnitude of the vector is invariant. The components of a vector change from one coordinate system to the next, as we will see in the following slides. So the components of vectors are not invariant under a coordinate change. As an example, let's consider some vector v. It has components, just restrict ourselves to 2 dimensions, it has components 1, 1 in a Cartesian coordinate system. Now this, and here's a picture of it here. Now this could represent the metal bar. It is 1 unit long in the x direction, 1 unit long in the y direction in this coordinate system. Its magnitude, here it is square root of 2, so it would be square root 2 meters long. Now that's the solid metal bar is not going to change no matter what coordinate system we put in. Now this could be the coordinates of the velocity of an object. So the one here in the x direction could be 1 meter per second in the x direction, this could be 1 meter per second in the y direction, and this is the velocity vector. Or it could be acceleration, or it could be anything else. The point is the magnitude of the vector is constant. It's fixed at square root 2, and when we change to a different coordinate system, that's not going to change. If its length of the metal bar is square root 2 meters in this coordinate system, it'll be square root 2 meters in any other coordinate system, or square root 2 meters per second, whatever object that we're interested in. Let's rotate the space or the coordinate system by 45 degrees in an anti-clockwise direction to give the new Cartesian coordinate system x prime, y prime. So here it is, here's the same vector, but in the x prime, y prime system, it has coordinates v square root 2 in the x direction, 0 in the y direction. Its magnitude is still square root 2. It hasn't changed. We can rotate the space around it for a new coordinate system, but that doesn't change the magnitude or the length of the vector. The invariance of vectors refers both to their magnitude or length and direction, and not to their components, which can and do change under a change of coordinates. And here's our change of coordinates from xy Cartesian system to x prime, y prime Cartesian system. That simply involved a rotation of the coordinate axes. Same vector, pointing in the same direction, same magnitude, same length. Here we are, components. In the different systems they've changed, but the magnitude in both systems has not. Alright, in special relativity, 4 vectors that are defined to be invariant in their magnitude length because they are defined in relation to physically measurable quantities such as the speed of light or the rest mass of the particle, and we'll see that shortly. So the position 4 vector of some object in Minkowski space-time is given by this object here, time, and the position coordinates x, y, and z. Its magnitude squared is given by r dot r, is eta, the metric here, which I've not shown you, but in previous videos I have. So we'll have 4x4 matrix with -1 in the top left-hand corner, +1s down the diagonal, and 0 everywhere else. When we calculate that through, we end up with this squared space-time interval here. Alright, the speed of light is constant in all frames of reference are in relative motion with respect to each other, so any two observers in frames r and r prime will always agree that the square of their space-time intervals are equal. Because all observers agree on the speed of light being the same in all frames of reference, this space-time interval works out to be the same for all observers in relative motion. And that's the square of the space-time interval that we saw on the previous page. An observer in the r prime frame will have these coordinates, an observer in the r frame will have these coordinates. Both will agree on the magnitude of this interval here, which is the square of the space-time interval. The invariance of the magnitude of the four-momentum vector p is related to the fact that all observers agree on the value of the rest mass m0 of the object, irrespective of what transformation of coordinates it undergoes. And we'll see that shortly, but the momentum 4 vector here is given by the rest mass times the velocity 4 vector, or in component form E over c for the time component, and then for the spatial momentum components here. Alright, the square of that interval, p dot p, eta matrix again, 4x4, Minkowski metric, and here's the contravariant components of the vector here. Put this in action here, we get this object here. Here we go, and that ends up giving us minus e squared on c squared plus p squared. But we also have, as we saw earlier, the magnitude squared p dot p is this thing here, which is m0 squared times dot product of the velocity 4 vectors, which gives us minus c squared for that part. And so that coming back here, these two are obviously equal, this one and this one are obviously equal, and so this object here is equal to this one. And again, the invariance of the momentum 4 vector for all observers, so changing from one coordinate system, the prime, unprimed to the prime, all observers will agree that the momentum 4 vector has the form we've seen earlier on the previous page, and that remains invariant. And the reason for that is it's related here to the rest mass of the object. All observers agree on the rest mass of the object, and so it's an invariant quantity. So the magnitude or length squared of the momentum 4 vector, its magnitude, is invariant under a coordinate change. So vectors are invariant as geometric physical objects, but they are not invariant in their coordinates because these can change under a coordinate transformation. So the following picture may help you remember this. Here's our vector in the xy Cartesian system. Now rotate the space around it to give you a different coordinate system. You get the x prime, y prime Cartesian coordinate system. The magnitude of the vector is the same in both coordinate systems. It's just under the coordinate transformation, the coordinates change from 1, 1 to square root 2, 0. And that is that.